behalf of AirMet Scientific, I'm pleased to welcome you all to the fourth of this series of webinars, Headlines in Occupational Hygiene Air Sampling. Our presenter today really needs no introduction as she's so well known to the hygiene community here in Australia. So I'll now hand over to Debbie, who's presenting from her office in Houston. So over to you now, Debbie.
Okay, thank you, Peter. Well, hello and welcome to another edition of Headlines in Hygiene Air Sampling. Thank you very much for being a part of this transcontinental training event. As Peter and I were just chatting before getting ready for the event, we were saying, isn't it exciting that we can all get together and have this training event? But I also look forward to seeing many of you in person at the AIOH conference in Brisbane. Okay, normally I speak on air sampling methods and media, but today I am also going to discuss another important aspect of air sampling, calibration. So get ready to recalibrate your knowledge of sample pump flow measurements. Then we will get back to methods and media and discuss some aggressive moves in passive sampling. Pun intended, in case you missed my humor. Okay, so let's go with the flow and begin with topic number one. Here's the plan. First, we will take a moment to review traditional definitions and devices for pump calibration. Then we will look at the science of calibration and measurement with some terms used to describe standards in the field of metrology. Next, we will review the role of standards organizations and accrediting bodies in calibration testing. And I will end by introducing a new pump calibrator from SKC. Peter Shields will also address this topic by discussing calibration testing in Australia and services provided by AirMet Scientific. Now, as most of you know, I have been with SKC a very long time, 32 years to be exact. And throughout those years, I've occasionally received phone calls from folks brand new to air sampling who are a bit confused that their new pump wasn't, quote, calibrated. And they questioned why they had to actually buy a calibrator. So here's a slide of clarification if you too are new to occupational hygiene sampling. When I say calibration of a pump, I mean that you set and verify the flow rate of the pump to that specified in the sampling and analytical method being followed. This is typically done before and after every sample that you take so that you can advise the lab of the air volume. Okay, so I want to be sure we're all up to speed on that. Now, shown on this slide are the traditional definitions for standards that are found in the ACGIH Air Sampling Instruments book used in occupational hygiene. In short, primary standards base their measurements on the physical dimensions of an enclosed space. That has been our historical definition of a primary standard. The notable reference, Patty's Industrial Hygiene and Toxicology, goes on to say that these readings are unequivocal because they are based on measurable linear dimensions such as length and diameter of a cylinder. I would think unequivocal, yes, assuming you have a nice flat bubble and good hand-eye coordination on the timing, which I don't necessarily have at 6 o'clock in the morning. Secondary standards trace their calibration to a primary standard and must be periodically recalibrated. Now, shown here are calibrators that we all know that have been traditionally described as primary and secondary standards in our profession. But, as I took a second look at these long-standing definitions in today's times, I honestly had to ask some questions. First, I wondered, why is there no designated accuracy of a primary or secondary standard? There's just like a description. Secondly, I've noted that there are differences in our little profession from country to country on what is and isn't considered a primary standard. For example, US OSHA notes in their most recent technical manual that they no longer consider an inverted bubble burette to be a primary standard. And I've learned from my Australian friends that electronic calibrators considered to be primary standards in the US are not considered primary standards in Australia. So, I began a quest for knowledge, and I decided to dig into the field of metrology, which I've learned is the science of measurements. First, I went to the ultimate reference, right, Wikipedia. Wikipedia told me that every country maintains its own metrology system. So, okay, that could explain the differences in how we define various calibration devices from country to country. Secondly, I learned from this document shown on the slide that there are many different types of standards in this big field of metrology, including things like primary measurement standard, national measurement standard, industry-specific standard, and more. And none of these standards actually have a designated accuracy level like I was looking for. I found it particularly interesting that the strict definition for secondary measurement standard in metrology is a close match to that used in occupational hygiene. But the definition of a primary measurement standard in metrology is a bit more strict than that traditionally used in our field. Again, going back to Wikipedia, you can see the strict definition of a primary standard in metrology. It is a device that is sufficiently accurate such that it is not calibrated by any other standard. Their value is accepted without reference to other standards. By these definitions, it would seem that all calibrators commonly used in our profession would be considered secondary standards, since these devices are calibrated annually to a higher standard. But again, that has not been the historical definition used in our field. And wait, there's more. I've also just recently learned another definition for calibrators, this time described in the ACGIH Air Sampling Instruments book, as well as Patty's Industrial Hygiene and Toxicology. This is a so-called intermediate standard. I never heard of this. I have 30-some years in this field. An intermediate standard is a highly accurate secondary standard that provides an accuracy nearly comparable to that of a primary standard, but which of themselves cannot be calibrated by internal volume measurements. And it goes on to say that intermediate standards provide an accuracy of approximately 1%. So I was happy with this definition because I finally got a stated accuracy assigned to a particular type of standard. Again, 1%. Sorry. Now, the good news is that the science of calibration continues to evolve. You know, I can honestly remember my very first job in industrial hygiene. Right out of school, I worked for a government, a city government agency on a low budget, And when we would calibrate our old Bendix pumps, we had to go to the chemistry lab and take a burette. I made a calibration chamber from a pickle jar in the cafeteria, got some dishwashing soap, and felt highly scientific, honestly, and quite resourceful. Now, standards organizations and accrediting bodies have stepped into this area, thank God, to provide users more assurance of reliability, however you define primary and secondary standards in your country. At this point in time, calibrators are available with documented performance data, including accuracy, with certificates that verify traceability to a higher standard. Standards such as ISO IEC 17025 specify the requirements for competency and accreditation of calibration laboratories. And in a few moments, Peter Shields will speak further on this issue here in Australia. Now, the technology of calibrators also continues to evolve. I would like to introduce you to a brand new calibrator from SKC. Since many of our pumps incorporate the name AirCheck, this calibrator has been given the clever name of Checkmate. Or in Australia, we could call it the good on you mate. It is an orifice-type flow meter that uses a differential pressure sensor. Okay. Simply put, the delta P is proportional to the airflow. It has an accuracy of 1%, thus meeting the definition of an intermediate standard we've just all learned. This is our first model, and the measurement range is 0.75 to 5 liters per minute, so it's more a high flow calibrator. It is very small, thin, lightweight, and the price is lightweight as well. It has very simple operation using one button. Yay. Now, one of the most common questions that I get on this new calibrator is whether it calculates an average. The simple answer is yes, but let me tell you more. Other electronic calibrators take a series of single discrete readings. The bubble or the piston goes up the chamber, possibly with an added kerplunk, kerplunk, to tell you it's taken one reading. Depending on how many readings you want, it will then take an average at the end of all of the single readings. The Checkmate instead displays a moving average of the measured flow rate. Okay. And the averaging period is 2 to 3 seconds. So there's no waiting for the end of a series to take an average. The displayed reading is the average. Okay, and up next, I'll ask Peter to give a discussion of calibration issues in Australia and services provided by AirMet Scientific. So Peter, you have a word for us?
Thanks very much, Debbie. So as a follow-on from the first part of Debbie's presentation, I thought I'd give you a quick update on our service offering in this area. AirMet Scientific is now NATA accredited to ISO IEC 17025 for flow meter and air sampling pump calibrations. So with this accreditation, we can provide NATA endorsed calibration for flow meters such as the new SKC Checkmate that Debbie's just talked about, also Defenders, dry cals, rotameters or any other flow meters you may be using against the primary standard. So our accreditation covers the range of 200 mils a minute to 5 litres a minute and is for air. So we test at 5 different points across the range of the device, and this service is carried out in our Melbourne Calibration Laboratory. As part of this accreditation, we can also test air sampling pumps in accordance with the requirements of NATA's application document Annex B, so asbestos fibre counting. So under the workplace pump calibration section, for this service we generally do back pressure tests up to 7 different flow rates depending on your request. And for those of you who are doing asbestos monitoring, you might be interested that the testing we have done on the new SKC AirCheck Touch pump that Debbie just showed shows it has no problems meeting the NATA back pressure requirements of 4 litres a minute. The AirCheck Touch also falls under the classification of a direct automatic flow control pump, thus reducing the calibration frequency requirements under NATA. So if anyone's interested in these services, please feel free to contact your local AirMet scientific office. I'll now hand you back to Debbie for the final section of the webinar.
Okay, thanks, Peter. Okay, topic 2. We'll get back to media and methods. I will discuss some recent moves from US and UK regulatory and research organizations in regards to passive sampling. So we will specifically look at recent initiatives from US OSHA, US EPA, and the UK Health and Safety Executive. And then I will give an update on how SKC has responded to these moves. But first, let's begin at the beginning of passive sampler technology, the 1970s, my glory days. Those were the days of great music, great dancing, and it was also a great time in history for passive sampling. You may have heard of a Palms tube when studying occupational hygiene. Well, it was actually in 1973 that this researcher Palms and his colleague Gunnison developed the first quantitative sampler based on the principle of diffusion. And I always think it's such a coincidence that 1973 was the year SKC made the first charcoal tube for NIOSH. So that 1973 was a very big year for air sampling. Then in 1977, there was a so-called gas badge, a charcoal badge for organic vapors that was developed. And by 1980, 3M and DuPont introduced their own organic vapor monitors. Now, since that time, there have been a number of advances in the types of passive samplers commercially available and in the development of passive sampler validation protocols by several organizations shown here. More recent initiatives by US and UK agencies continue to advance the science and technology of passive samplers. So let's take a look at some of these things. First, from US OSHA, a unique approach to validating passive samplers, which led to the publication of government agency methods and acceptance of passive samplers for compliance sampling of designated compounds, of course. Recently, from US EPA, a new regulation that requires fenceline monitoring of benzene at petroleum refineries using diffusive thermal desorption tubes. And new in 2016 from the UK Health and Safety Executive, MDHS Method 104. This comprises 3 different methods for sampling VOCs, including one that specifies, again, these diffusive thermal desorption tubes. So we'll discuss each of these. So let's begin with US OSHA. It was actually in the late 1990s that things started to happen. OSHA took an important step in both advancing the science of passive samplers and using the data from these devices for compliance. Their efforts at that time focused on how to determine the overall error of these devices. Now, in the U.S., all sampling and analytical methods used by OSHA themselves, OSHA inspectors, must have a sampling and analytical error designated, what we call an SAE. The SAE is used with the air sampling results to determine if employers have exceeded the allowable limit. So until OSHA could develop a way to measure the error of a passive sampler, their inspectors could not use them for compliance testing. Maybe you have a similar type thing in Australia. Now, for active sampling, OSHA incorporates the flow rate variation for a sampling pump in their SAE determinations. And normally, this is plus or minus 5% for the flow rate variation. So, in my opinion, they had a very clever idea to experimentally determine the sampling rate variation of various models of passive samplers. And this would be a comparable parameter to pump flow rate. Once they documented the sampling rate variation of a passive sampler, essentially the error associated just with the sampling portion of the procedure, they could combine this with the error associated with lab analysis to determine the total error, the SAE. Now, believe me, this was a huge breakthrough in the use of passive samplers for compliance testing in the U.S. OSHA studied various brands of passive samplers to determine the sampling rate variation. And their studies revealed that the variation of the SKC 575 series, now called the VOC check passive sampler, was 8.7%. This value was deemed acceptable and was used to move forward in the validation of sampling methods for designated VOCs. Similar studies were done on the SKC UMEX 100 for formaldehyde, and this led to the development of a new passive sampler method for this compound. Once OSHA developed a way to calculate the overall error, they could proceed in developing complete, validated methods for target compounds using passive samplers that could be used by compliance officers. On this slide, you can see the compounds for which OSHA has developed sampling methods using passive samplers. Another scientific advancement from the U.S. OSHA validations is the use of passive samplers for short-term sampling. Now, historically, it seems passive samplers have been used only for 8-hour TWA measurements. But now, OSHA methods designate minimum sample times of only 10 minutes for some compounds. So this allows for the collection of stale samples using passive devices when specified. Again, a big breakthrough. Like US OSHA, SKC research chemists have been advancing the science of passive sampling through laboratory validations. In recent years, SKC has done validations using the 575 series samplers for methanol, anesthetic waste gases, ethylene oxide, styrene, and most recently siloxanes. Why did we select these compounds? Because SKC customers in various fields like fracking, healthcare, and general industry came to us and asked us to validate these compounds. SKC has also done validations using the UMEX series samplers for various aldehydes, sulfur dioxide, nitrogen dioxide, and ammonia. And right now we're looking at ozone. Now let's move on to a new U.S. EPA regulation for fenceline monitoring of benzene from petroleum refineries. You know, living in Texas as I do, this is a subject near and dear to my heart. Researchers at my old alma mater, University of Texas School of Public Health, have studied benzene levels in these lower economic communities surrounding refineries in the Houston, Texas area. The focus of this new EPA regulation, I think, is very, very interesting. It is fugitive emissions, which go largely undetected. Since they are not emitted through a stack or a vent, the pollutant levels are difficult to measure directly, basically are unknown. Examples of fugitive emissions are things like equipment leaks, pressure relief devices, tanks, wastewater handling and treatment. So, why did US EPA focus on fence line monitoring of benzene in this regulation? Well, here's why. EPA notes that 85% of benzene emissions from refineries are fugitive ground level sources, 85%. The highest concentration of fugitive emissions outside the refinery occur by the property boundary near ground level. So, air sampling at the property boundary can provide a direct measure of the annual average concentrations surrounding the refinery. Now, stainless steel canisters have been the primary sampler used for VOCs by environmental professionals. But canisters are not typically suitable for sample times longer than 24 hours. And this new EPA regulation specifies sample times of 14 days, continuous sampling. So for this application, they specify the use of passive or diffusive thermal desorption tubes. And for this application, EPA Method 325 was put forth. There are two subparts to this method. They call it A and B, 325A, 325B. And they cover the various aspects from sampler design, sampler placement, sampling, and analysis. The sampler they specify is, again, the passive stainless steel tube, and US EPA has even specified the sorbent, which is Carbopac X. The tubes are placed inside of a shelter to protect them from rain and debris, and they are deployed again for these continuous 2-week sampling periods. After sampling, the tubes are thermally desorbed for GCFID or GCMS analysis. And the regulation requires corrective action by the refinery if they exceed a concentration of 9 micrograms per cubic meter, or 2.8 ppb, based on an average of 26 2-week readings. SKC, of course, now offers these passive thermal desorption tubes to meet this application and more. The 3.5-inch stainless steel tubes are compatible with thermal desorbers from Perkin-Elmer or Marks International. The samplers are made inert with a specialized procedure, and they come with swage lock screw caps. For user convenience, of course, they have, again, a unique identification number and a sampling arrow indicator, just like is specified in EPA TO Method 17 for active thermal desorption tubes. Like all thermal desorption tubes, they are reusable for a number of times. I would normally typically say you can hit them with heat maybe 20-25 times before the sorbent begins to break down. But the laboratory can best determine when the sorbent inside the tube is no longer usable. As you may know, SKC has previously developed a passive sampling badge called the Ultra, which has the option of thermal desorption analysis by transferring the sorbent from the badge to a thermal desorption tube. Now, the larger area, the face, if you will, of the Ultra sampler is much bigger than the little face of a tube. So it has a much higher uptake rate of 16 milliliters per minute for benzene, compared to 0.67 milliliters for benzene using the passive tube. Again, 16 milliliters a minute compared to 0.67. Now, this higher uptake rate is an advantage for low-level detection at sample times of 24 hours or less. But since Method 325 requires a 14-day sampling period, the passive tube with a lower uptake rate is specified by EPA. So again, there's applications for each of these samplers. Okay, and finally, in June of this year, the UK Health and Safety Executive released a new method, MDHS 104, for VOCs. This method is comprised of 3 subparts shown here on the slide. Part 2 describes diffusive sampling using thermal desorption tubes like those I just discussed in the EPA method. Oops, sorry. This new HSC method, honestly, is a beautiful method. It provides some very useful and detailed information, particularly in the tables. On their Table 1, they list recommended sample times for various expected concentration for each of the 3 method options. Beautiful, beautiful table. Table 4 lists uptake rates for many compounds using the passive thermal desorption tubes. So you have a lot of sampling rates for many things, not just benzene. So have a look at this method, which is online. I provided AirMet a link to this method and to other pertinent documents from OSHA and EPA. I gave you a link to the US OSHA Index of Sampling and Analytical Methods, which you can search by compound, and I gave you a link to a PowerPoint presentation developed by EPA that talks again about these facts and figures related to fugitive emission of benzene at petroleum refineries. So again, thank you very much for your attention. If you have further questions, again, just email me at skctech at skcinc.com. I answer all those myself, and I look forward to seeing you all again in Brisbane.